start off by looking at the syllabus really quick. Today we have Chapter 2, Sections 10 through that we're supposedly covering, but I'm going to actually take some time to cover a little more at the beginning of Chapter 2. And so we're going to push off everything a day, which means this bridge project we will not get started until probably Friday. So today and Wednesday we'll finish up Chapter 2, and then Friday we may end up talking about the bridge project on Wednesday, but probably wait till Friday. The bridge project is going to be coming from the project parts kit, I guess you could call it, and tool kit that I've given you. And for Wade, that should be coming still in the mail. It probably will come FedEx, actually. It's taken me a while to figure out how I was going to send that to you because the situations have changed over here on this campus, how we mail things, and so I had to do it differently. But anyway, point is that that should hopefully be in FedEx today and get to you maybe Wednesday or Thursday at the latest, hopefully. If it's not there by Friday, then we'll push it off, starting that project till next week, and we'll just make it work. But anyway, we'll spend at least the first part of this week finishing up Chapter 2 and talking about different types of engineering and some of the different traits of engineers in their fields. And then we'll move on to actually doing some engineering for a couple of weeks. And then we'll go back to the book, and we'll learn some more about engineering, and then we'll go back to projects for a couple of weeks, and then we'll go back to the book and back to projects. Essentially, we'll go back and forth like that the rest of the year. You can see here, we get through Chapter 6, and once we're through Chapter 6, we end up doing project after project after project. And that's kind of what we're shooting for, is to learn as much as we can from the book, and then just do a lot of projects and put things into practice doing engineering projects. We're going to go back in the book today. So what I'm actually going to take you to today, in the book in Chapter 2.5, it talks about engineering disciplines and related fields, and they have all kinds of charts and lists of different things, different types of engineering. And it goes on for pages and pages and pages. It talks about professional engineering and formal education for engineers and all these things. What I'm going to do is I'm going to show you a series of videos that I have tracked down and found from the National Science Foundation. And they're actually videos about different engineering fields spoken about by the engineers themselves. I find them interesting and engaging and informative. And so I'm going to go ahead and start these. And I may stop them from time to time to make some comments. Otherwise, we're just going to watch some videos today and learn about engineering. You can find these on my YouTube page. MPCC Engineer is the name of the user, and you can find this playlist there.
Engineer Ken Moschke loves living and working in the city of Chicago. And from Ken's viewpoint, it's the structures that help bring the city to life. Every day, he gets to move to the pulse of a city filled with vitality, or ride, or climb, even skate.
Just in time.
Ken is a licensed civil engineer at Thornton Tomasetti, a world-renowned engineering firm.
Civil engineering is really the jack of all trades of the engineering profession. It includes transportation, structures, what I do. There's geotechnical, construction, water resources. Together, it's mostly about the infrastructure that we all use and we live in.
Civil engineering goes back to the earliest days of civilization. If anyone's responsible for building this country, it's civil engineers.
Civil engineering is really a people-serving profession, especially when nature throws us a curveball. When it comes to hurricanes, tornadoes, earthquakes, civil engineers are there to make sure that buildings, the bridges, and the infrastructure stays operating and stays safe for people.
Ken and his team specialized in structural engineering.
Very simply put, structural engineering is making things stand up. already in my career, I've worked on a huge variety of projects. I've worked on baseball stadiums, football stadiums, practice fields. I've worked on high-rises here in Chicago and even internationally in Denmark and in the UAE, in Dubai. The architect usually gives us a pretty picture of the skin of the building. The structural engineer really looks beyond that into the guts and the bones that hold up that skin.
The team is on their way to one of Chicago's most beloved icons. Rising from the ashes 17 years after the Great Chicago Fire, the Rookery Building was completed in 1888.
Many times we get involved with historic construction and trying to preserve it. At the Rookery Building, we're going in, evaluating the existing structure, and trying to come up with new ways so that crews can keep it in top shape.
The walls follow masonry variables, and the interior is all steel construction.
In the drawings, the civil engineers see a story of imagination and innovation.
Pretty cool.
Elevators, electric lighting, plate glass windows, fireproofing, features that define the modern skyscraper. Ken has a desk, but you'll rarely find him there.
Let's open up the drawings and see if we can find out what's going on. Looks like there's a step here, so I'm betting you see how they have the two beams adjacent to each other. And one of these is going to be high for this part. This is going to be that load or snow load on it.
Then it's off to a presentation. Remarkably, Ken's day has just begun. Ken grew up on a farm, so you'd think the big city would mean a big adjustment. But in just a few short years, he's developed a special connection to the city.
One of the reasons I went into structural engineering was because I wanted to be able to show people what I worked on. I've worked on that building over there. Here's another building I've worked on. Another one on this side of the river. We worked on the Chicago Board of Trade building too. When I was in high school, I didn't know necessarily that I wanted to be a civil engineer. I was good in math and science, but I think the best engineers are those that are very well-rounded and bring together a lot of different ideas.
Some of Ken's projects involve routine structural maintenance. Others push structural design to the limits.
Imagine putting a 50-story building on top of Union Station. That's what structural engineers do. This meant that we needed to look at all the existing foundations and the columns and imagine a way to support the weight of a new structure on top of what was already there.
What most folks don't see are the design challenges that Ken has to face.
If a wind gust were to go and hit the building, this is the behavior that it would most likely start to move in. If it moves too quickly or too much, people might get sick, and then there's no way you could sell space on the top floor.
A city would not be a city without buildings like these, or without rail lines, bridges and roads, water and sewage systems. Things people count on to keep their city working.
There's a lot of work that's involved with maintaining all of these parts of the infrastructure. And I guess engineers need to be a little more Clark Kent than Superman.
That's why civil engineers don't just work with companies like Ken's. You'll also find them in municipal, state, and federal government settings, research facilities, and universities. Ken holds Bachelor of Science and Master of Science degrees in civil engineering.
Very rarely do I work on anything by myself, but together that helps us to come up with the best solution to the problems.
In a sense, their job is to pave the way for the future by incorporating new materials, building techniques, and new ways to save energy.
This is a project that I worked on with some architects, trying to envision a way to use a currently undeveloped site in Chicago. We think the idea that we're presenting with green technology offers a way of the future, how buildings in the future will need to be planned and designed in order to be more sustainable in our infrastructure and in our cities.
Green ideas like these are changing the way buildings are being built and renovated all over the world.
I think there are so many other difficult questions in today's day and age dealing with the environmental impact of the building, how to deal with the building's energy needs. engineers can be more involved with all aspects of that. Instead of just taking the skin that they give us for granted, let's go back and try and engineer a better way.
Ken sees Chicago as a living city, ever evolving and ever in need of improvements.
There's always something new to work on. It's wonderful having that feeling that all your hard work is paid off into something tangible.
As he looks out into the future, Ken can see there's no end to what he can learn and what he can do to help cities like Chicago thrive.
So I really like that one. Let's move on to the next one. Got that already.
When I put my effort to it currently as an engineer,
This is for mechanical engineering.
research and rescue. My name is Nate Ball, and I'm a mechanical engineer. My job as an engineer is to use what I know about the world, what I know about how things work, to solve problems.
As a mechanical engineer, Nate pushes technology to its limits by using his knowledge of motion and energy to develop all sorts of mechanical devices, including a new vaccine delivery system called the VAC.
About 4.3 million deaths are caused every year by vaccine-preventable diseases. And a major challenge in getting vaccines to the appropriate places in third-world countries is being able to keep them at the right temperature. Vaccines have to stay, in general, about 4 degrees Celsius in order to stay frozen. And to get vaccines at that temperature into really rural areas with spotty electrical power is a big challenge. This device here is a portable vaccine refrigeration backpack. It's like a refrigerator you wear on your back that allows you to take up to 1,200 vaccine doses into a rural area that doesn't have room. So in a situation where you've got major infrastructure devastation, like in a huge earthquake in a third world country, a device like this has great potential to make a big difference because it can take massive doses of antibiotics and needed medicines into rural areas that have no power in order to be able to deliver the needed medicine.
Nate spends much of his time refining his designs and building models and prototypes to get products ready for manufacturing.
What we're looking at here is a 3D model of an older version of the backpack that's actually created inside the computer. So in engineering, if you're building a complicated system, it's very useful to build a model like this in order to visualize how all the parts will actually attach together.
Nate shares his passion for engineering by mentoring others. He even hosts a TV show for PBS called Design Sprint.
So on the show, I get to mentor a couple of teams of young engineers and introduce challenges to them as week to week they split into teams and hear from a client, kind of like real engineers do. And the client says, hey, Design Squad, I need you to build this for me. I need you to solve this problem. I want you to build me the fastest strengths are possible. And the kids on the show actually go out and do it. All right, so we got our board-keeping part. We're going to have a 6-foot coil rebar.
When he's not inspiring future engineers, Nate can often be found helping athletes reach new heights.
I actually coach some of the MIT pole vaulters here, and I'm also a pole vaulter myself, and I have been since about 6th grade. It's kind of cool because coming to pole vaulting from an engineering perspective as a coach, I get to describe basically what's going on in a different way that other pole vault coaches might do it. So where the box is, you want the bar to be back away from it so that when you peak, you're not going to fall back down to that skid that the kids don't want. The neat thing about engineering is that it allows you to solve all kinds of problems, ranging from building cool things like dragsters and bridges and skyscrapers to solving interesting, complicated problems like how do you get a drug directly into your skin without using a needle.
When a natural disaster or a fast-moving epidemic strikes, a needle-free injection device could save countless lives.
So a project that I've been working on is a controller device, instead of using a gas-powered piston to fire, actually uses a controllable actuator. So you can dial down the power in real time to inject milk with a person or a child, and dial the power back up for a person with tough skin. The advantage of that is huge because you can imagine having a delivery gun that's got a very large vial of vaccine. You can line up a whole bunch of people and just put it up to each person's arm and shoot right down the line and inoculate a huge amount of people in a very short amount of time.
Nate's a busy guy, even during his downtime.
Because the physicality of getting up and doing stuff with your body is a nice break from your brain. And being in some kind of shape physically kind of helps us work harder mentally during the run. We really enjoy getting out there and working hard, flipping upside down, and sort of, I guess, applying some kind of physics understanding to what's actually happening in the air as we flip your rod and flip in the air, obstacles, what have you. Engineering by no means is all fun and games either. It's never going to be a straight-through process where you come in, see the problem, oh, I know something. You may not even have consensus in your group as to how to solve the problem in the first place. And you're working with limited resources and limited time. So persistence is a very important aspect of being an engineer. I love solving problems, and I love that engineering is a creative job. There's a whole world of things to invent and create and work with people, and so you're never bored as an engineer. A couple colleagues of mine who are also engineers are working on a pretty cool project. It's called the Tourbot. What that is a robot that's designed to rove around halls of MIT giving tours.
While we're building a system that's giving tours of the MIT campus, we're not necessarily only trying to figure out how to build systems to give tours. We're trying to see how you can get robots that interact with people to really be able to serve people and interact and change people's lives.
Additionally, the navigation system we put on the robot is pretty state.
We use a variety of sensors. We have laser range finders that we use to find obstacles around us. We have a camera that looks at the sky to green markers that we place there that identify the robot where it is.
Those sensors could have implications for robots in other scenarios, like hospitals or work sites, or museums, libraries, whatever. What I'm working on right here is a preliminary design for a robot brain, which you could add to a robot similar to a Tourbot in order to make it do something like pick up an object off the ground or even open a door. It's a multi-degree freedom system, which means similar to the human arm, it's got a lot of different joints that can function in several different ways.
Nate also manages to find time to engineer some jazz improvisations.
It incorporates a lot of stuff I like about engineering in the kind of a free-flow process of coming up with new ideas, but it's in real time on the keyboard, but it's also really relaxing. Engineers can make a very good living, and the reason is the world always has important problems to solve, and the world will always need engineers. The things I love about engineering are that I get to work with other engineers that are passionate about solving problems and helping people. I get to see my work directly benefit people, and I always have a reason to keep learning and to find my new knowledge and new interesting problems to solve. In 10 years or 20 years or at the end of my life, I'd love to be able to look back and say, I've spent that time making people's life better. That's what I want to do.
Electrical engineering now.
Turning on the burst. Have you guys looked at the data of how I make it? It's really fun to be able to touch something and think of something and solve a problem that no one has ever been able to solve before. Do you have any way of plotting what the optimal frequency is for each one of the positions?
I can try.
My name is Yale McGuire, and I am Chief Technology Officer at Thing Magic.
Yale has been building things since he was a kid.
I remember when I was about 12 years old, and I really took an incredible interest in designing and building radio-controlled vehicles.
And now, designing and building things is his job. like this little piece of technology that's starting to make a big difference.
This is a tag. This is an RFID tag. RFID stands for radio frequency identification. These are invisible waves that communicate information from one point to another. Look, just hit this tab.
Yale and his team make the readers that take the information stored on the tags, send it to a computer.
We can use this to identify objects uniquely and have a computer understand what those objects are by just sticking them on there. The main problem that Ford was trying to solve was people would have to travel for a long distance to get to a particular job site, and if they got to that site and they realized that they had forgotten their drill saw or something like that, they'd actually have to go to a local store and buy one, and those things are really expensive.
These tags will let a pickup truck know which tools are in the back and which ones aren't. But that's just the beginning.
Basically, having access to information and more information about objects allows us to be more efficient about how we transport them, manipulate them, handle them.
Produce traveling from the field to the store, for example, can be affected by changes in temperature. RFID tags might just be the answer.
With special types of tags like this that can actually record temperature, maybe it will mean that we can send this product out such that when it actually reaches you, it's fresher and newer and tastier.
While electrical engineers are problem solvers, using their high-tech understanding of circuitry and electronics can take a long time for an idea to come to life.
Typically, to make a product that can survive all of the difficulties in the real world, it takes about a year.
Which can be long hours of meetings, designing, building, and lots of testing.
So I do a lot of work. I'm certainly not complaining because I have so much fun having to pick and choose between these different things. I just wish that there were more hours to play.
But Yale does have some time left over for other kinds of fun.
In fact, it's actually, I think, a good thing to be able to take a break from what I'm working on, be able to focus on something, keep my mind focused on one particular activity.
Which helps him focus even better on the projects that mean the most to him. Like the one he's working on with a nonprofit he co-founded called Design That Matters.
And this is really just to show that the concept is possible, and then later on we'll help experiment with.
They design products especially for use in developing countries, like this prototype of a low-cost infant incubator.
We want to make something that's easy to use in developing countries and will save children's lives.
Used for cars and other common machinery, Yale and his team developed a life-saving product that's not only low cost, but most any repair person or auto mechanic can keep it running.
I think part of why I'm excited about engineering and science always is to be able to look at a problem, spend some time with it, work with colleagues, and then finally figure out how to solve it. Finally solve one of those problems, one of those big problems with such an incredible skill. Life's too short to not pick exactly what you want to do and do it. Try to just work towards that and work as hard as you can to realize that goal.
And for engineer Yale McGuire, it doesn't get more exciting than this.
I chose a career that I knew I was passionate about and that I was going to love for the rest of my life. Hey, you're in.
Next,
She runs a research lab.
biomedical engineering.
She teaches at a university.
You're not plated down on table.
And she's co-founder of a nanotechnologies company.
So what we're looking for is feedback from you.
Living by the wisdom of Yoda, biomedical engineer Michelle Kine is all about embracing life.
The problems that we work on, these are important problems. There is a possibility that we can really make a huge impact on people's lives. That's a great motivator.
Biomedical engineers like Michelle combine biology, medicine, and engineering to design and develop new equipment and methods that improve the quality of human health and life. They design everything from surgical devices, prosthetics, and artificial organs, to systems for medical imaging, patient monitoring, and diagnosing disease. They also develop new medical procedures and research solutions to clinical problems.
I get to teach and work with students and work at a university. And I also get to have a company on the side and work with industry, so I feel like it's the best of all worlds. Yeah, it works really well, and I'm looking forward to getting this into the hands of students and researchers.
Michelle has pioneered advancements in manufacturing medical diagnostic chips, a new technology that miniaturizes lab testing. Initially, the chips, which have microscopic grooves for moving samples like blood through a series of lab tests, required expensive equipment and took a long time to make. Remembering her favorite childhood craft, Michelle got a crazy idea.
So I was playing, as I usually do, in my kitchen one night, and I realized that if I took shrinky dinks and I patterned onto the shrinky dinks, when they shrink down, I could use the features on the shrinky dinks to create my microfluidic chips. So these are pre-stressed thermoplastic sheets. So you can imagine it's sort of like a rubber band that's stretched out and then frozen down, right? So when you heat them up, the polymer chains relax and they go back to their relaxed state, so they shrink back. To be perfectly honest, it was really hard in the beginning. I came up with this idea and we published, I tried to convince my students to use a children's toy for their science. And they were like, people are gonna laugh at us.
But people didn't laugh. The invention went viral on the internet and catapulted Michelle into the spotlight. Scientists from all over the world were now interested in Michelle's lab on a chip.
If I treat one patient, I can treat that patient. But if you come up with a medical invention, a technology that can save hundreds or thousands of lives at once, that's, that would be really cool. So this small size here is 1.5 microns. Width of your human hair is about 150 microns. So this is about 1/100th the width of your hair. So they have the EBs, and then how do they apply to different chemicals?
Michelle and her research team have also been working on ways to grow embryonic stem cells into heart muscle cells.
Once we create these cardiomyocytes, we need to figure out how to maturate them so that they're functional heart cells. A day in the life of me. I usually play soccer with my dog in the morning, and then I walk to work. I come in and I work with the students, and we work on coming up with new crazy ideas and writing papers and working on grants. I have a company on the side, so I work with a company also. We're trying to commercialize our first 2 products this year. Hey Mark, ready to meet?
Good. Yeah.
As scientific founder and a member of Nanotechnology's Scientific Advisory Board, Michelle helps research and develop new biomedical technologies and products. She also looks at ways to improve and expand the benefits of existing product lines.
I like to tell people that I make accessories. I'm still a girl. A big part of my lab is focused on developing point-of-care diagnostic devices. Our goal is to be able to bring really inexpensive plastic chips to the developing world so that we can detect and then therefore treat infectious diseases early on. We're meeting with the chair of the pediatrics department at the medical school here because he's very interested in bringing these technologies to the real world.
And so if you can even have a screening test that can be done at the bedside.
It's a neat job because you don't, checking in the morning with somebody, you don't check out, right? You decide what problems are important to you, you work on those problems, and you police yourself.
Like many engineers, Michelle tends to think about her work 24/7, so she stresses the importance of balance in her life.
I love to play. I also discovered a new sport called acro yoga, which is basically 2-person yoga, and you can do, flips and aerials, and it's really fun. I used to be big into biking. We built a human-powered vehicle when I was at Berkeley.
In fact, Michelle holds a land speed world record for a bike she helped design and build in grad school.
Being able to really have the conviction to carry it through to the end, knowing that it might not work, is very difficult. But I think I'm an optimist at heart, and so that kind of keeps me going. Feels like a cooking show.
Michelle holds a Bachelor of Science and Master of Science degree in mechanical engineering and a PhD in bioengineering.
I decided to become an engineer because I was really bad at math and science. And I thought that if I studied hard enough and I worked on it enough, that I'd get good at it. So I did a summer internship in biomedical engineering when I was 15, and I loved it. It's hands-on, it's real world. You feel like you're making a difference. You're not solving problems that other people have solved before. These are brand new problems that people need answers to. That's cool.
Biomedical engineers work in hospitals, universities, industry, and labs. They work with physical scientists and engineers, clinicians, life scientists, chemists, and medical scientists.
I think biomedical engineering is extremely collaborative, and I think that's what I love best about it. What is that?
Yeah.
Have you ever seen that deposited on metals before?
Let's see what that scale, no.
It's this culture of working together and talking with each other and coming up with new ideas and forming these collaborations, even if they're on the other side of the world. Your world feels very close. You don't feel isolated at all. It's been a great ride. It's far exceeded any expectation or dream I could have ever had. It's been really fun. I've gotten to go give talks at really cool places, Vancouver, Hong Kong, the Caribbean. I was invited to MIT for the Tier 35 award, which is really exciting for me. It's been amazing. I was real fortunate to have gone into biomedical engineering. I can't imagine a better job in the world. See? You never believe me.
Just got a couple more here. See how many we can get through.
I think oftentimes the public takes for granted that they have clean water.
So this is environmental engineering, which is kind of a subset of civil engineering.
But that's something that people are working very hard to ensure. We want people to have confidence that that water will be healthy. They don't need to buy bottled water. My name is Tamar Losleben. I'm an environmental engineer with Malcolm Parney, and I work in New York City. Environmental engineering is really where public health and environmental needs meet. Environmental engineers work with cleaning up contamination or preventing contamination of the air, soil, and water. We study where there could be an impact on the environment or people's health, and then we create solutions to try and mitigate that impact.
Tamar's area of specialty is water engineering, specifically water treatment.
So, I'm here at a friend's house, and I'm here to test lead in the water, because often in these old houses that were built maybe 50 or 100 years ago, there's concern about lead in the water. I'm collecting samples to make sure that the water is safe. At Malcolm Parney, I work on a lot of different types of projects, anything from determining water storage needs or disinfection needs, upgrading drinking water facilities or wastewater facilities, doing overall master planning. I also look at sustainability of projects, and that's something that we're very much focused on now. I'm working on a project in Nassau County in Long Island at the Bay Park
sewage treatment plant. We're working with the New York State Department of Environmental Conservation to meet the stricter regulations that they have put on us to remove the proper amount of chlorine and dissolved oxygen from the wastewater leaving the plant and entering the water bodies. So Tamar is working with us here to monitor the levels of the dissolved oxygen and the chlorine.
Working for an engineering firm provides Tamar with an opportunity to work on a variety of projects and to spend lots of time outdoors, which she loves.
I like to start my day outside, whether it's running or surfing in the morning or biking to work. My working environment is a mix. I sometimes work in the office. Other days I'll head to the field. I quite like my hours that I work. It's usually a 40-hour week. We're here at Meadow Lake in New York City, and I've taken a sample of the lake water to test for turbidity. I basically want to understand if there are a lot of particles that are suspended in the water. It's about 30, which is higher than what we would want for drinking water, but for swimming and for recreational purposes, that's fine. We're in Jackson Heights. This is the little indie of New York City. I love it here. There's so many cultures, so many colors, and it reminds me of my childhood. I grew up in India, Kenya, and Egypt. There's just so much here.
Living in large international cities, Tamar has seen firsthand how important it is to balance urban growth with preserving and protecting the environment. She knew early on that this is how she wanted to make a difference in the world. She devotes much of her time to organizations like Engineers Without Borders.
People can learn how to make it and reconstruct it, and if it breaks, it costs about $10 or $15 to.
It's accessible also. So, and that's a very good solution. That's a very good innovative solution.
In El Salvador, I worked with the community that built one of them, and they still use it.
As a project lead for Engineers Without Borders, Tamar has worked hands-on with team members and local communities in constructing water storage, distribution, and purification systems for small villages in developing countries. Tamar is passionate about sharing her experiences with like-minded colleagues.
About half of the population in developing countries lack access to proper sanitation, or even just improved sanitation. They don't have a latrine to use. And 1 out of 6 people don't have access to an improved water source. So they're drinking water that could potentially make them sick, or they could even die from. I know as an environmental engineer that I impact people's lives, and hopefully they're healthier because of that. When I work abroad, I see the impact directly. It changes people's lives. They now have a water tap, or they're not getting sick. And we can talk about it. I can see it. I can see their joy and how thankful they are.
Like many water, Tamar finds herself both working and playing in and around water.
We're at Rockaway Beach in New York, and we're heading out to the ocean to see if there's some little waves to catch this morning. When I'm surfing, I see a lot of marine life. I've seen porpoises, and I see whales. Pretty big whale, I don't know what kind, but it jumped in the air twice and just went down. I also love to bike around the city, into Central Park, along the rivers, and I sometimes bring my paints. I grew up really intrigued by nature and found that I just had this desire to try and capture some of the beauty. Environmental engineers are very much optimists, and I think sometimes we're confused for idealists, but it's just that we see an issue or something that could be mitigated, something that's damaging the environment or people, and we have ideas of how to solve that problem. And it may not be a perfect solution at first, but we return to the problems and we keep on working on them. And I think that's the hope that we have, is that things can be better.
Environmental engineers like Tamar are experts in pollution control, industrial hygiene, hazardous waste management, water supply, radiation protection, wastewater management, public health, and land management. They may work in engineering firms, universities, private research firms, corporations, testing laboratories, and government agencies of all types.
I would say someone who wants to be an environmental engineer should have an interest in people, and in science and be strong in math. We use a lot of chemistry. We do calculations on dosages, on flow rates, but I think someone who has a strong interest in science and people would be a good environmental engineer.
Environmental engineers typically hold a Bachelor of Science degree in civil, mechanical, or environmental engineering. Most continue on to get a master's degree in environmental engineering.
Engineering is a field that has historically been dominated by men, but I do see that changing in my generation, and I'm encouraged by it. My supervisor's a wonderful woman engineer, great leader. My dream is to work abroad on international water projects to help people get better access to clean, safe water. Water is a need that is global, and I think that need will be there, and so will environmental engineers.
Environmental engineering. Let's take a look at this materials engineering.
One of the most rewarding moments for a materials engineer is seeing the product being produced on a mass scale. My name is Carlos Barrios, and I'm a materials engineer.
Materials engineers like Carlos work with the structure, properties, processing, and performance of different materials, or stuff, in order to engineer new and improved stuff.
So that's what makes my job so dynamic.
Since everything in the world is made of stuff, there's no limit to what kinds of materials engineers might invent or reinvent. Materials for biomedical applications like artificial skin and prosthetics, high-performance composites for aerospace, even materials for sports equipment and apparel.
You'll find materials engineers working in 3 different venues: government, academic, and corporate environments.
Carlos designs and develops sticky stuff.
As a materials engineer, I'm part of the adhesives group of 3M. So what we do is study different adhesives, and we stick to different surfaces. One of the big things for adhesives is using adhesives that last longer, are more resistant to environmental conditions, and can be used in a very small amount. We try to develop new films, thinner films, using technologies as nanotechnology that uses very small particles or use materials that are coming from a biological source. So once we have these new materials, we use them into commercial products.
High-tech adhesives engineered at companies like 3M are used everywhere, from in the home to aerospace, architecture, construction, electronics, and automobiles.
We interact every day with people from different disciplines.
Bubbles coming off indicate that the byproduct is coming off, so the reaction must be going. Looks like everything's going just like we expected.
During the development process, products go through several stages before full-scale production can begin.
Most of the times we start in the bench. We make the material, we characterize it, and we start making very small hand spreads. But once we have these new materials, we prepare films that are becoming new adhesives.
And in this area, you can see the little spheres you were describing. And it turns out they're not fully covering the surface, but they are present.
My wife also works in the materials area. And we like jogging, running, and in Minnesota we have very nice parks and very nice landscapes.
No matter where he is, Carlos is always thinking about stuff.
When you go to nature, you can see, for example, leaves. Leaves are highly structured surfaces, and they are self-cleaning. So one of the projects that we use now is to try to mimic these properties of the nature to incorporate them into the new products of the future. It is crucial to understand the physics and the chemistry at the surface. You can see here that we increase the volume of the droplet. The droplet basically is sliding at the surface. In some cases, we have very strong requirements in terms of the strength of the material. So we have very specific tests to make sure that we are under the specifications of the design application. One good example of that is the impact test.
Yeah, we have an impact tester that we're able to test at
a variety of different conditions, so we can look at very cold conditions, which sometimes make plastics very brittle, and then we can also take it up to higher temperatures too to make sure that it has the wide range of performance that you need.
Once we find the optimum conditions for the materials that we use for this film, we go to the pilot plant. In the pilot plant, we simulate in a very small scale what is going to happen in the factories.
So this is the roll. It looks very nice.
It has a very smooth pull off as well.
We need to hear the customer because he or she is the one who's going to use it. So for this, we use focus panels.
I'd say the red one is probably the toughest one to unwind. It stretches a little bit when you're unwinding it.
What we have now is a green light to go to the factories and start making the product in a commercial scale.
Like most research engineers, Carlos loves a good challenge, even when he's not working.
Rustier. Rustier. Rustier.
My car has been with me for a few years. It's getting old, but I can detect the problems from the materials perspective and try to get to a solution. So something that makes our work at 3M very interesting is that we are a global company, and we have labs and production plants in every single spot of the world. For a materials engineer, it is very important to know what's going on around us, not only inside of 3M, but outside.
In the decades to come, materials engineers will be at the forefront of solving problems on a global scale, engineering next-generation fuel cells, solar cells, water treatment systems, even new drug delivery techniques for fighting disease.
One of the main impacts of the job of a materials engineer is coming with new solutions, for example, for environmentally friendly materials. By doing that, we're replacing materials commonly used, for example, from oil, and try to green materials.
Materials engineers typically hold a Bachelor of Science degree in chemical, mechanical, or materials engineering. Most continue on to get a master's degree in materials engineering.
I worked for a while as a process engineer, but then I wanted to go deeper in the properties of materials, and I obtained a master's and a PhD in polymer science.
When everything has a place to go, it's easy for kids to stay organized.
I'm very pleased to see some of my materials going to scale production. One of the focuses of my career is to develop adhesives that stick to everything, so something called a universal adhesive.
Take a good look at your stuff. Materials engineers like Carlos are working hard to make all our stuff even better, at home and around the world.
Okay, let's move. That's the end of my playlist, but they do have some other ones that they've added. They've got, for example, a chemical engineer is one of the newer ones. I don't know if they've got any more engineers on the NSF thing. They do have chemical engineering as well, but there's lots of other people out there on YouTube that are putting up these videos about different types of engineering, and there's just a ton of different types of engineering. So I recommend that if you have a particular type of engineering that you're interested in, that you go look for a video about that type of engineering, and then maybe get online and look for other things involving that type of engineering. It can really help you to decide what your interests are, where they lie, and the kind of things that you might need to be doing in the future as you go towards that type of engineering. That's all I have for you today. There is still homework from Chapter 2 to do, so make sure you're getting that done. And we will come back to the rest of Chapter 2 on Wednesday. Have a good day.